Hey guys, so I'm back right where this all began, Letchworth Woods, right on campus. I thought it was a good opportunity to come to our old stomping grounds and to talk about multi-cohort stands. So in today's lecture, I'm going to be focusing on these multi-cohorts, and I'm going to definitely mention minor disturbances that drive the development of multi-cohort stands. I'll talk about successional attributes, then I'll get into specific details about Western New York forests, looking at Wang et al. In 2009, and then finally we'll get into these wildlife trees. So why don't you come in to Letchworth Woods with me, and we will talk about multi-cohort stands. Again, this is lecture 18, and I'm excited to be out here today. Trout lily of the year, like flowering. So pretty. So in last lecture, we talked about single cohort stands. So as a quick refresher, a single cohort stand develops as a major disturbance comes in a forest. That major disturbance kills all or most of the trees in that area, and you get these 4 stages of stand development that follow. Now in today's lecture, we're focusing on multi-cohort stands, and in a multi-cohort stand, you have that area driven to be a multi-cohort stand when there are minor disturbances involved. Minor disturbances kind of reduce smaller areas of trees, leaving those legacy trees untouched. So there are multiple individuals from different cohorts inhabiting the same larger area, but within that larger area there are these pockets where these minor disturbances rolled through. So in our own backyard, a disturbance that would drive a single cohort stand to later become a multi-cohort stand is something like a small surface fire in which thin-barked species would die. So maple and beech have thin bark. They can't withstand fires. Their fire kills, these fires kill the cambium around the circumference of the individual, and once the entire vascular cambium is removed or killed, that individual is going to die. So these fires actually select out those thin bark species, and that is essentially a minor disturbance, with oak individuals with thicker bark being able to live and prosper after that minor disturbance. In the positions where beech and maple were living, you get a new cohort developing in their space. So this is an example of a minor disturbance in our own area. Now in the southwestern of the country, we have that spruce budworm, and those individuals select a specific species in which also does an analogous thing in that side of the country. So these species-specific disturbances definitely drive the development of multiple cohorts. This is a black cherry, and you see there is debris in here. There's some insects. This is amber in the making. So if this gets buried for long enough, it'll actually turn into amber. There are several reasons why a tree produces this resin. Sometimes it is a infestation of insects, sometimes it's a bacterial infection or a viral infection. But whatever the cause, this defense gives us a little information. There are specialists that look at amber. They look at the individuals trapped inside. Here we have an isopod here. They can actually chemically test the amber and better understand what species created it. So I thought this was a cool example to come across.
So I want to talk about minor disturbances and their interaction with cohorts. So depending on when the minor disturbance occurs throughout these different forest stages that we learned about last lecture, you are going to have separate outcomes. For example, if a minor disturbance occurs during the stand initiation phase, then you're not going to get a separate cohort. The stand initiation phase is just going to be prolonged, and you're just going to have a single cohort develop. Now, if a minor disturbance occurs during the stem exclusion, something else may occur. Now, we're looking at two separate types of minor disturbances right now. So if a spatially extensive minor disturbance occurs during the stem exclusion phase, then you are going to have a separate cohort develop, and you are going to have a multi-cohort stand as a result. However, if minor disturbances that are species specific roll through that area, this is not going to result in a multiple cohort, because a species specific minor disturbance is going to kill just those small trees, and those small trees that are removed are quickly going to be filled in by the crowns of adjacent trees. So again, remember about the stem exclusion phase, this highly competitive phase in which adjacent species are just waiting for little gaps to open up so they can quickly fill in. So again, if a species specific minor disturbance happens, you're not going to have a multi-cohort stand develop. Adjacent species are just going to grow in those open spaces. Now, if minor disturbances occur during the stand reinitiation stage or old growth stage, those minor disturbances will result in new cohorts if the disturbance covers a large enough area or kills enough trees of one species. So this is kind of, foolproof in the terms of multi-cohort stand development. If these minor disturbances, if they're large enough, they're going to create multiple cohorts. They will open up enough space that multiple mature trees can eventually survive, again, causing these multiple cohorts to develop.
So I want to take this time to actually talk about the differences between these multi-cohort stands and old growth forests, because the lines are a little bit confusing. So an old growth forest, again, it depends on the species that live there. Remember, because it's not considered an old growth until all of the individuals from that initial stage have actually died. So again, on the west coast, we have these giant sequoias that live to be over 2,000 years old. Areas that are dominated by giant sequoia trees are not going to be considered old growth until those individuals that first were initiated have all died. So you're not going to get an old growth forest in those systems for at least 2,000 years. Over here, we have the oldest living species. Many of them are white oaks that live around 300 years old. So we're not going to have true old growth systems after an initial disturbance for about 300 years. So the difference I want to talk about is the development of multi-cohort and old growth forests is about the types of disturbances. Obviously, a single cohort is initiated by a major disturbance. We already talked about that. And a multiple cohort stand is driven by more minor disturbances. Additionally, it's important to note that those minor disturbances are of external forces. So things like wind, things like insect outbreaks and parasites and pathogens are all considered external forces. Minor external forces drive multi-cohort stands. Old growth forests, they develop when there are internal forces at play. So these internal disturbances include individuals that just die of old age and individuals that are excluded via competition. So those two factors are internal forces. Those drive the development of old growth forests, and we have external minor disturbances driving multi-cohort stands. So basically, you can take a look at an area within a forest and see if it is a true old growth or if it's a multi-cohort stand, depending on the size and the spatial arrangement of the trees you're seeing. So a multi-cohort stand is going to have a patch of a forested section that is going to be made up of different height individuals. So they're going to be surrounded by maybe taller individuals, and just think of a minor disturbance coming in, killing a small stand of trees, and there's just a section of a different age group, a different cohort. If you look at an old growth stand, you will see individuals of all different ages, because those minor disturbances, those internal disturbances, are much smaller than the minor disturbances that drive multi-cohort stands. So in an old growth system, you're going to have a single individual tree die of, let's say, old age, and that small patch eventually will allow new growth to form. So there's going to be more heterogeneity in these old growth forests, meaning that different patches, really isolated small patches, are going to be made up of different aged and sized individuals, whereas a multi-cohort stand, you're going to have just sections of that forest that are going to be made up of totally different cohorts. So in terms of multi-cohort stand development, we have several ways in which that stand can develop. Number one is advanced regeneration. So little saplings, little seedlings, if they're not disturbed, they will fill in those gaps, and they will get larger and eventually mature into that cohort. There is the sprouting from stumps or pre-existing roots, and there is the germination of buried seeds. So in this next section, we're going to focus on that advanced regeneration. With these existing stems that have lived through this minor disturbance, you're going to get faster growth with this more available light. So that's one. With this additional available light, you're going to have these stems grow and mature, but there are several things that are dependent on those stems actually maturing. For one, it is the growth rate of that species. We know that different species are going to have different growth rates, especially if they're sun-loving or if they're more shade-tolerant individuals. So the likelihood, let's say a sugar maple will reach maturity, depends on two things: the growth rate of that species and the gap size created by that minor disturbance. Now it's important to note that a 20-meter gap can allow several seedlings to inhabit. But in reality, a 20-meter plot will only allow one mature individual to live there. So that's important to note, that you can have all these seedlings, but think about the mature stage of that species. So you're going to need either larger minor disturbances that open up gaps larger than 20 meters squared, or several of these smaller gaps throughout the entire forest.
To paint this picture more vividly, let's take a look at this figure on the right here with this red vertical line running through it. Now this is the annual height increment as a function of total height, and we could see that at 8 meters this sugar maple is having the fastest growth. So it is growing taller the fastest when it is at 8 meters tall. Now, if we were to look at the lateral increment on the figure to the right of this, we can see that the highest rates of lateral growth occur during its juvenile stage when it is 5 meters tall. So both of these ideas should kind of be familiar to us, as this figure on the bottom certainly depicts these two ideas. We looked at this figure back in lecture 9, and we learned about these patterns. So during the mature phase, you're going to have exceedingly rapid vertical growth, whereas during the juvenile stage, you're going to have more horizontal growth. Let's now look at two separate scenarios. So let's say there is a minor disturbance that leaves a 10-meter gap. Now a canopy tree will fill that 10-meter gap in about 30 years. And you can see this depicted on the histogram below. So you have that 10-meter gap, and in around 30 years, you have the filling of that gap by that canopy tree. Now a 2.5-meter gap will be filled in less than 5 years. So in a mature forest, let's say the mature forest is 25 meters high, which is 81 feet. A 2-meter tall sapling has a 0% chance of reaching and becoming a part of the canopy in just a 2.5-meter gap. So if you take a look at this figure on the bottom right, you will see the initial height. So we have this 2-meter individual, and in a you can see it has a 0% probability of reaching that maturity, of reaching that canopy with just a 2.5-meter gap. However, in a 10-meter gap, we can see that number, that red dot, around that 30% mark. Now, if we look at an 8-meter sapling, it too has a 0% chance of reaching the canopy in a 2.5-meter gap, and its probability increases to around 70% in a 10-meter gap. This truly reveals something really interesting about forest ecology, and that is the importance of gap size. So although 30% to 70% seems like a stark difference, the main number that we need to focus is that 0%. So basically, we have two vastly different individuals. One is a 2-meter sapling, the other is already 8 meters tall. In a small enough gap, in a 2.5-meter gap, either of them is not going to reach maturity. So gaps, right? The importance of gap size truly shines through with this figure on the bottom right. Now, the average gap in maple forests has a diameter of around 20 meters. And although I mentioned this idea in the clip before this, I'll just touch on it really quickly again. So basically, that 20-meter diameter is enough for many different saplings to grow. But when we zoom out, only one mature tree can actually fill that space. So although, you might see a minor disturbance and you see all these saplings, and I see this all the time hiking in the early summer, I see all these maples that just carpet the floor. And so many of them are not even going to make it to the next year. You would think that, if we were to get a time machine and move 80 years in the future, that blanket of maple seedlings that would turn into this really dense maple forest. But that small area, although you have all these seedlings and saplings, only one individual can take up that space. So again, highlighting the importance of gap size. So we see these 20-meter gaps, and in order for there to be a new cohort, there needs to be a larger than a 20-meter gap, or we need several of these 20-meter gaps to be riddled throughout the ecosystem to allow enough mature individuals to inhabit that space.
So I want to talk about these canopy gaps associated with apical control. So trees with weak apical control, they're going to fill gaps quickly. They're going to grow fast and robustly and shade out other understory species. So for example, sugar maple has weak apical control. It leafs out and it spreads its branches horizontally, rapidly, covering all these understory species. Now, I had to look around, and I'm on the edge of Letchworth Woods, close to the road here. You can hear a lot of cars, but I came here because I did see a stand of red pines, and as we know, many conifers, including red pine, have strong apical control. So species with strong apical control, they are not going to fill in these gaps rapidly, and they are not going to shade the understory trees. You can just see, even though the hardwoods have not leafed out yet, you can see all of these branches, these horizontal branches created by this gap right on the edge of this forested habitat. These hardwoods with weak apical control, they are spreading out their limbs rapidly. They are taking this opportunity to absorb this available light. And the strong apical controlled species like this pine, they can only spread out so much. You could see its canopy, and it's, even though there was this opportunity to acquire more light, if you are a species that has strong apical control, you're just not going to, compete in terms of light availability like many of these weakly apical controlled hardwoods. So we talked about the canopy trees in their relation to apical control. Now let's talk about the understory trees as a function of apical control. So understory trees with weak apical control, they do not grow vertically rapidly, and so they have lower success of reaching the canopy before it fills. So weakly apical controlled trees do not grow vertically rapidly, and they are going to have a lower success reaching the canopy before it fills. Now, understory trees with strong apical control, like this red pine behind me, they do grow vertically rapidly, and so they have a higher success of reaching the canopy gap before it fills. So that's an interesting idea. Mature individuals who are already at the canopy, they're not going to compete that well when a gap opens up. But juvenile trees with strong apical control, they're actually going to do better than their weakly apical controlled counterparts because they allocate more energy towards this vertical growth. So some interesting trade-offs there.
So let's take a look at this multi-cohort stand in Virginia. So looking at this specific stand, researchers analyzed tree ring data. Looking at these data, they realized that there was 2 specific time periods in which the annual rings got wider than average for several decades, suggesting that something happened to the forests at that time. So these forests are comprised of multiple cohorts, with the oldest trees being established at around in the early 1700s. So we have this red oak being this early dominant species. We can see this histogram above here. These researchers looked through the records of the time and found that a large storm around 1800 opened up the forest. Obviously, more light penetrated, and tree rings have a wider growth pattern during this time with all this available light. Along with this time period of exaggerated growth, you also have new cohorts being developed at this time as this storm removed large patches within this forested region. The chestnut blight, which reached this area in 1910, reduced and killed all of these American chestnuts. So I talked about this chestnut blight a few lectures ago, or was that last lecture? I already forgot. Now this chestnut blight removed all these American chestnuts, and especially in this specific forest, and south of this forest, you have chestnuts absolutely dominating these ecosystems. Many times, 1 out of every 4 trees along the Appalachian Mountains have this dominance of chestnut trees. So 1 out of every 4 trees was usually a chestnut tree. With the blight coming through, that blight clearly is species specific, and especially when you have a dominant tree being reduced, that will provide more than enough space, more than enough gap area for new cohorts to come up. So we have the storm and we have the chestnut blight. The cohorts establishing after 1800 and 1910 both show a prolonged establishment occurring over several decades that corresponds to the time that the forests remain more open, as evidenced by this tree ring width. With this study, these researchers realized that this specific stand was certainly a multi-cohort stand instead of a transitional old growth. So in a previous study, we looked at those white oaks from a similar area, and those white oaks in West Virginia, they did show continuous establishment of shade-tolerant trees over the past 200 years due to continuous death of white oak trees, and thus was an example of old growth forests. So in this Virginia system, these 2 discrete disturbances drove the multi-cohort stands instead of having more internal disturbances, more internal interactions like trees dying from competition and old age. You actually have these 2 separate disturbances driving multi-cohort stands.
So I want to talk about successional characteristics. These are recurring themes that we've seen throughout this entire course, and we should be really familiar with cottonwoods. I use cottonwoods as an example all the time. And species that are first to arrive in a specific ecosystem after a disturbance, we can call them early successional species. Species that succeed those initial colonizers we call late successional species. So cottonwoods, again, these are sun-loving individuals. They show up, they grow up, and they die in a relatively fast fashion. They only germinate in full sunlight, so this is a huge filter, an ecological filter that we see. When you see cottonwoods, when you see a stand of cottonwoods, you know that the area was disturbed, and you're going to have, you're going to be witnessing an early successional forest. Now, a late successional species is, again, an example that we see throughout this entire course, the American beech. They are shade tolerant, they grow extremely well in a full forest, and they don't really enjoy full sunlight. So you're never going to see an American beech stand in an open habitat, really. So they really do reveal a forest that is further along this successional trajectory. So we can talk about seeds too, and how certain seed characteristics have evolved with these different species carrying out these different life histories. So cottonwoods, again, for example, they disperse vast distances. They are tiny little seeds that have those fluffy cotton ball like vibes to them, and they fly for miles. Again, they only germinate in full sunlight. And then we have American beech seeds, we have oak acorns. Those seeds are larger. They don't disperse as far, but they are dispersed by mammals and other animals. So you see the differences in seed characteristics. In a closed forest with species that are shade tolerant, that are further along the successional trajectory, you're going to have more individuals that entice different animals to disperse their seeds. In closed forests, you're going to have more animals. So that is a trait that I really like to see. I like finding these patterns in nature. Now, after a community is completely disturbed, there's going to be fewer animals, and you're only going to get those wind dispersed seeds. So early successional species usually have those tiny wind dispersed seeds. Now, there are a ton of trade-offs involved with seeds. For example, the smaller the seed, the larger its dispersal area, but usually the smaller the seed, the lower the germination is. So if you were to plant 100 acorns and 100 cottonwood seeds, many more acorns would germinate just because there's more reserves for that embryo, and there are more defenses in those acorns. If a certain parasitic or pathogenic fungi or bacteria get into the cottonwood seed, that seed is totally just donezo. So these trade-offs that we constantly see through nature that are really interesting and intriguing. The last characteristic I want to talk about is the characteristic of the tree stems. So black willow, for example, they are an early successional species. They carry out their life cycle rather fast, and because of that, their stems grow exceedingly fast. They grow tall and wide, faster than many species that I've encountered today. Cottonwoods too have a relatively fast growth rate. Longer lived species that are more shade tolerant, that get their start in a closed forest, they're going to allocate more energy towards these defensive compounds to allow them to live their longer lives, whereas sun-loving species like cottonwoods and black willow, they're going to not allocate those reserves towards antifungal and all these different resins and all these different compounds because they're just going to mature fast, and then they're going to die. Their life cycle is much shorter than these longer-lived shade-tolerant species. So those are some characteristics I think are worth mentioning in terms of these systems. So Wang et al. In 2009 wanted to better understand the composition of forests in western New York by comparing more recent data collected in the early 90s to pre-settlement European data collected in the 1700s. So the Holland Land Company, they came in, and to invoke European settlers to come to this area, they wanted to analyze the layout of the land and let them know which areas, what species dominated these specific areas. So the Holland Land Company, they carried out this early survey, and when we take these data and compare it to more modern data, we see some interesting species interactions. So number one thing is when we compare these two data sets, we see a stark decrease in American beech. Now this is no surprise, since American beech is it's a shade tolerant species, and in the eastern side of this country, forests dominated by beech are mainly forests that are of old growth nature. You're not going to have early successional forests having dominant individuals of American beech. So obviously, as time progressed, as these European settlers came in and altered the land, they transformed many forests into agricultural settings, which made more light come in those systems, and you have a stark decrease in American beech. So these beech trees, they used to comprise 40% of these forests. Nowadays, beech only makes up 10%. Now, the second most abundant species in pre-settlement times is the sugar maple, and its numbers have relatively stayed the same over this vast area of data collected. So sugar maple is around 20% at both times, and that's an interesting idea because both sugar maple and beech are these shade tolerant species. The one difference that we have is that we actually can get resources from sugar maple in the form of maple syrup. So people obviously realize this, and they may have cleared sugar maple stands, but they didn't really want to because they wanted to tap those stands for maple syrup. So it's interesting to see this human interaction. American beech, it didn't really provide anything towards these humans, so they got rid of them, and as a result, you see this stark reduction in beech through time. So another pattern we see by comparing these two data sets are the increase in more sun-loving species like poplar, these cottonwoods we keep talking about, and ash trees. Ash has become much more abundant in recent times, not so recent times, and we'll get to that in a second, but sun-loving species have done really well since this pre-establishment time period. Now this is because these human disturbances, the removal of forests, has opened up this canopy and allowed more sun to penetrate. You get these clearing of forest, you get more area of edge habitat, which again receive more light than closed forests. So of course these sun-loving species are going to do great. Now ash has encountered another perturbance in more modern times, known as the emerald ash borer. We talked about this in a previous lecture. This Asian insect has reduced many of the green ash and white ash of this area. So that actually allows more of a multi-cohort establishment as individual species are selected against because of this invasive insect. An extremely interesting takeaway from this awesome study is that our systems are actually very close to reaching their old growth status. Unlike the West Coast, unlike the systems dominated by giant sequoia, those systems, they require a lot of time, a lot of effort, and a lot of money to allow those systems to maintain their ecological longevity. You need a fire regime in place in the West Coast, whereas here, our ecosystems, they'll actually return quite readily if we just leave them alone.
Researchers came to this conclusion because when you plotted the data received by the FIA, which is the Forest Inventory Analysis, that 1990 data set of forest cover on the y-axis, and you graphed it with the Holland Land Company data of the late 1700s on the x-axis, you got these figures, and basically the closer the black solid line is to the dotted line means that the closer those stands are to those data of the pre-establishment forests. So we can see in early forests, the solid black line is nowhere near the same, has nowhere near the same R squared as that dashed line. But as forests progress, as they become older and older stands, the species composition actually is very reminiscent of that pre-establishment. So I like these figures, which truly highlight that if we do not touch our ecosystems on the East Coast, we can attain that old growth status of the pre-establishment forests.
If we just leave these systems alone, succession will ensue. You'll get these sun-loving species over time shift to more shade-tolerant species, and you'll get this old growth system that we saw before European settlers came in. So it's a kind of interesting idea, and it fills me with some hope, knowing that all we have to do is protect land and allow time to carry out the succession of those forests. So lastly, I want to talk about wildlife and wildlife trees. So what exactly is wildlife? Well, wildlife is made up of animals that are not domesticated, that are living in the wild. Good name. Wildlife trees are trees you also find in the wild that wildlife tends to inhabit and utilize throughout their life cycle. Many species that live in the wild, many animals, they require trees in some part of their life cycle. So the functions of these wildlife trees vary. Many times they're used for nesting sites, for resting sites, which are kind of one and the same. Other times they are used for feeding. Think about a woodpecker feeding on the grubs inside this old old beech tree. Storage. Many of these wildlife trees are actually used by animals to store nuts and seeds throughout the winter. And finally, you have hunting. Many predators in this forest actually perch on wildlife trees to get a better view of the forest floor, which actually increases their kill rate. So we have those different ways that wildlife utilizes wildlife trees. Now, all wildlife trees aren't treated equally, meaning that certain species with certain attributes are actually better for wildlife. So in an old growth, you're going to have wider trees. You're going to have larger trees at DBH, and those are going to be more inhabited by wildlife. Their area is going to be bigger. You get fungi like these species, Fomes formentarius. You get these individual fungi break down the heartwood of these individuals. You can actually feel it's hollow in the middle. I mean, I can feel it. I can hear it too. These fungi over time, they hollow out this tree, excavating cavities for different wildlife to live inside. Obviously, larger individuals are going to be more selected by these different organisms living here. Early successional species are also going to be more selected by wildlife for a few reasons. Usually, they're going to be there no matter what forest you're in, because forests have been utilized by humans for so long. You're going to get edge habitats. You're going to get development, encroaching human development on the edge of those forests, leading to more of these early successional species, these cottonwoods, for example, getting a foothold on those edge habitats. So there's just going to be a lot of early successional species. That Western New York example we talked about, you can see the shifting of shade tolerant to more sun loving species. That's just a trend we see in the Anthropocene. So another reason why early successional species are going to be selected for is that these early successional species, they are sun loving, and they have that live fast, die hard kind of life. They grow fast in the full sun, and they generally live short lives. So these species, they don't invest in resins and antifungal compounds because they're generally going to be dead in around 100, 150 years. So these short lives, trees that live short lives, they are not going to invest in defensive compounds. However, you get different species. For example, bristlecone pine, the longest living species on the planet, over 5,000 years old, right? Those individuals, they grow slow. They reach maturity at a very old age, and to make it to their old age, to make it to maturity, they have to invest a lot of energy in different resins and different antibacterial and antifungal compounds to stand the test of time. So wildlife is going to tend to select, those primary successional species because they grow fast and they don't pack their wood with resins and antifungal compounds. They don't hollow out they hollow out more easily compared to more old growth shade tolerant species. A more recent understanding is staring us right at the face, and it's the importance of these snags. So these standing dead trees are actually vital for many wildlife organisms living in these forests. These snags, they create cavities, and that's the main A main use of these dead woody substrates is this nesting site. This very old snag, this dead beech tree, it's covered by fungi, which I mentioned, that has essentially hollowed out the inside of this dead individual. I'm looking at this side. There's all these different, and I'm going to get a close-up in a second. There's all these different holes where different insects have burrowed in and have carried out their life cycle. And then on this side, we have a ton of bird poop, which suggests that there has been some recent nesting in this tree. So this idea that these snags, must be removed, especially with logging. Loggers will come in, and if a tree dies because of, how they're manipulating the forest, they'll take the snag out. And this recent understanding has let us better interact with these forests by leaving some of these stands behind, because they do have a very positive ecological functioning.
So this study provides us with really concrete evidence. So we can look at this figure, and it just shows more in-depth interactions and helps us better understand these forest ecosystems a little bit better. So in this study, they looked at different species on this y-axis, and you see that these researchers studied both living stems on the right and dead stems on the left. Right off the bat, you can see, and if we realize the colors associated, those red colors are associated with individuals that have a high importance to the surrounding ecology, a high value of importance. Ultimately, you can easily see that the dead stems are going to have more importance, more ecological importance. That is because these dead stems, they hollow out fast, and animals, they like these hollowed out areas. So we already talked about that. Now, when we get into the size, you can see that the diameter, as diameter increases, usually you're going to have a greater importance. Like you and I don't like tight spaces. I don't like being cramped up in a small room. Animals too. They are going to want to compete more so for a larger hollowed out tree. There's more space. There's possibly more structural integrity. They're just more important to ecosystems. So we can see that trend too. Finally, when we look at the different species, we see that other trend. So we have black spruce, which is a later successional species. It doesn't have that much importance because it's that slower species. It grows slower. Because it lives a longer life, it packs its wood with antifungal compounds and resins, so it can carry out its long life cycle. With these different resins and different compounds, it is less likely to be hollowed out. And if it doesn't hollow out, animals aren't really gonna, care about this species. We look at this bottom here, we have this aspen, and you could clearly see that it is just really important it has a lot of ecological importance because it has that other life history, that live hard or live fast, die hard, gets into the ecosystems, full sunlight, grows fast, doesn't worry about longevity, doesn't allocate energy towards these compounds. So it breaks down fast. It's more likely to be hollowed out. So it has this higher importance factor.
Now these dead snags, they truly do enhance biodiversity in these forests, especially when you find dead snags of all different stages of decomposition. This very old American beech. It is rather decomposed, and I've been sitting here watching it for just a few minutes, and already I've seen about 7 different insect species flying in, crawling around it. There is a colony of carpenter ants living within it. I'm seeing all these species of bees surrounding it, so I think there might be a hive nearby, and just really does highlight the importance of these dead snags in old forests. So this concludes lecture 18, and this is the last lecture of the semester, and I just again wanted to thank you guys. It's been one heck of a ride. I think we all did our best during this pretty crazy situation. You guys have definitely been one of my favorite classes to teach, even with our short time together. I'm really looking forward to your blog articles. I'm really looking forward to help you and guide you in the right direction. And some of you, if you're in the area, I'll definitely be emailing you folks about summer hikes once this COVID-19 human interaction kind of settles a bit. I would love to go out and survey some forests with you. Thanks again for everything, and stay safe, be happy, and continue learning about forests. So yeah, I will catch you guys later.